as we look ahead, we need to know a few things, and the last thing that we covered was info from and equation. And so we did problems that had the equation as part of, the equation, how about that? Okay. And so what did we get from the equation? What did that allow us to do in terms of doing problems? What did we take from the equation? Do you remember? Oh my goodness, that was days ago. I don't know. What was this?
Said 2 whole days of break
has destroyed our total understanding of all chemistry. Okay. In terms of what we got from the balanced equation, first it must be balanced. And what it allowed us to do is relate 2 different compounds within the conversion from one thing to another. Okay? And so what we did was we took the numerical values of the coefficients and we said that in some sort of equation, so many moles of substance A can be converted into so many moles of substance B. Okay? And in the last equation that we used and calculation that we used, it says if I burned C6H12O6, it was a sugar, and it has a balanced equation that I show in step number 2. And I had 1 gram of the sugar and I burnt it. How much water is produced? The key was this. For every 1 full sugar, I will make 6 waters. Okay? So that was the key that we got from the balanced equation. Now, converting grams to moles is something that we use the molarity, the molar mass or the formula weight, and we used that twice. That was something old, but this is something new, the conversion factor from the balanced equation. And so, the one other thing that we understood is that we have to get to moles because that is the ratio that we look at within the balanced equation. And so we're going to do a lot of use, or we're going to use the molar mass quite often to get to moles so that we can do calculations. And so, this is early in the morning, but we're going to make you think. Get you going. Work with some partners. I want you to work on some of this. All right? After this worksheet, we only have 2 more concepts to learn in this chapter. And we will be done with all the concepts, and we will do lots of practice afterwards. But this is fundamental. We're finishing that chapter. Okay. First one, the decomposition of, what is that? Potassium chlorate, okay, is commonly used to prepare small amounts of oxygen in a laboratory. How many grams of oxygen can be prepared from 4.50 grams of potassium chlorate? Or potassium chlorate, sorry. And you were given the additional view that I actually gave you the balanced equation. Okay. So, what in the world did you do? Well, where do you start? That's kind of easy because there's only one number that you're given, so that's where you have to start. Okay? And So that's 4.50 grams of potassium chloride. So I'll help you out. There's where you start. And you're going to multiply it by something. Ultimately, this is no different than any conversion. You're just using different conversion factors. Okay? You have to remember, what's your first conversion factor going to be called? What are you going to use? this with somebody with a group. Okay. Anybody get this number? 1, 2, 3, 4, 5, 5. Okay. As you go through this, what's given is where we start. Okay. And so we have to reference everything from the whole compound, potassium chloride. Then we've got to relate potassium chloride to oxygen. The only way we can do that is 2 moles of this will produce 3 moles of oxygen. But to get there, we aren't given moles. What we're doing is giving grams, and so you have to convert grams into moles. Okay, and to do that, you use the molecular weight. And so if you look at potassium to 2 decimal places, 39.10. The chlorine and the oxygens to create a molecular mass for that, and then a molecular mass for oxygen is each oxygen is 16 times 2. And so in this, grams of the potassium chlorate cancel each other out. The moles cancel each other out of the potassium chlorate. Moles of oxygen are gone, and grams of oxygen are left. All right. When you do this in CHEM-111, you must use the molecular mass calculator for everything to work out because CHEM-111 is picky. Okay. Next thing. Okay. Solid lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide. The lithium hydroxide reacts with the carbon dioxide to form lithium carbonate and liquid water. How many grams of carbon dioxide can be absorbed by 1 gram of lithium hydroxide, given the equation? Again, this is a very simple one because it only gives you 1 starting place. So that lets you know at least you're heading in 1 direction and you know where to start. get that number? Okay. Now, what was different about this one than the last one? The last one we related a reactant with a product. This one, we related a reactant to a reactant. That doesn't matter. We can relate any two things in this equation. You don't have to go from one side to the other. You just have to make a relationship between those two things. All right. Now, let me show you something. All right, the homework for this one is equation 2. I'm going to work the assignment. All righty. Look at number 7 here. You can't quite see it. Okay, so here is an equation that I have to work. It's an unbalanced equation. It has iron 3 oxide plus aluminum creates iron metal and aluminum oxide. Okay. At the beginning of this reaction, you use 25.92 grams of iron 3 oxide and 9.85 grams of aluminum. What is the theoretical yield? And theoretical yield. That's a good term to know. What we just calculated in your last two examples was what's called the theoretical yield. On paper, if everything reacted perfectly, that's what you should get. Okay. That is theoretically what you should have. Now, is life real? Do we always get theoretically what we're supposed to? No, we'll deal with that in concept a little bit, okay? So, if you start with this, what number do you start with? In my last problem, I gave you one number to start with, right? What do you start with here? It gives you 2. That's a problem. Usually, in a problem, we give you one starting place. But if you take a look at just about every one of these, it's going to start you in 2 places. Okay? That leads to a totally different type of problem. Okay? In terms of what we're going to do, and that problem is called a limiting reagent problem. Okay? This is more like real life. You're going to mix 2 things together, and you're going to produce a product. But normally, you add in one that is a limiting reagent and one that is a excess reagent, or a limiting reactant and an excess reactant. Okay? Now, what in the world is the limiting and what is the excess? Okay? One of those 2 things that you're adding together is going to limit what can actually be made. The excess is the one that you just add in enough of to make sure that it reacts completely. Which one do you choose to be the limiting reagent? The expensive one. Which one do you choose to be the excess? The cheap one. Okay? And that's how we approach this. But limiting reagent. Okay, so here. Very simple problem. The sandwich example. I have 10 pieces of bread. I'm going to give it an elemental symbol of BD, and I have 7 pieces of Oscar Mayer bologna. I'm going to give it the designate OM because my bologna has a first name. How many sandwiches can be made? Okay. Well, first a bread plus Oscar Mayer bologna equals a sandwich. 2 pieces of bread with 1 piece of bologna in the middle. But that is unbalanced, so I will have to balance it. Now, 2 pieces of bread have to come with 1 Oscar Mayer to create 1 sandwich. Okay. Now, here's the deal. I have 2 starting points. I have 10 pieces of bread, and I have 7 pieces of bologna. You know which one's going to limit the reaction. Mathematically, I can calculate that. 10 pieces of bread, every 2 pieces will make 1 sandwich. I can make 5 sandwiches. 7 bolognas. If I take 1 piece of bologna for every 1 sandwich, I can make 7 sandwiches. Which is going to run out? Which reagent is running out first? The bread. In these problems, I have to do two separate calculations, okay, to the same endpoint. In this case, I made sandwiches, okay? And the limiting reagent is the one that produces the least because it will run out. These theoretical calculations assume this, that based upon the bread, I have unlimited amounts of bologna, and I'm going to use up all the bread. And then when I look at the calculation from the bologna side, I assume there's an unlimited amount of bread to create how many sandwiches I make. Okay? That is way too simple an example, all right, to do this. But the steps are the same because you could do this in your head. Okay? If I look at this picture, what is the limiting reagent? Well, the reactants are oxygen and hydrogen. So we're narrowing it down to one of those two things. Which one runs out first? Hydrogen. There's oxygen left over because in the end, I still have some oxygen floating around. If by chance I had more hydrogen, I could make more water. Okay, the reaction was hydrogen plus oxygen create water. Okay, it creates water and oxygen. Oxygen is just the excess reagent. It was just not completely used up. Okay, a lot of pictures and a lot of examples will be perfect, perfectly balanced, everything's used up, everything is nice and tidy, but in real life, very rarely do you ever react the exact two amounts perfectly to get a final solution. Now, we will do some examples like that in laboratory, but it's harder than you think, okay, to actually do a perfectly balanced reaction. Usually there's something left over. Okay, you could do the sandwich example in your head, but these were what the steps we went through. Okay, we're given some sort of amount of reactants or products. We either can be given an amount in grams or moles or micrograms because we can do some conversion factors. Okay, we have to predict the products if needed. So we had to predict what a sandwich was to do that. Then we had to balance that equation, and we did. Then you convert all amounts of reactant to a potential amount of products. All right? Usually you get to choose that. All right? In CHEM-111, it will usually say it will produce something. So calculate to that one because that saves a step. Okay? But two separate problems get two separate answers. Number 4, this is the hard part. You got to think. Identify the reactant that makes the smallest amount. Okay? You laugh when I say that's the hardest thing, but a lot of times this is where people get tripped up. That is the limiting reagent. You can then do more calculations based upon that limiting reagent, and I'll show you that in a moment. What we might ask is how much excess reagent is left over. Okay, and I'll show you how to do that in a moment. Now, here is a real-life example that you can't do in your head, but you might actually head in a certain direction. Okay, the two gases that react are nitrogen and hydrogen to react to form ammonia. Okay, that's what that common name of that NH3 is. If you had 1,250 grams of nitrogen and 300 grams of hydrogen, which one is the limiting reagent? Obviously, it's the one that's least, right? 300 is going to run out before 1,250 all the time, right? Okay, standardized tests, that may or may not be true. You can't just look at the grams at the beginning. If they're allowed to react, how much ammonia is formed and how much excess would be left over. Okay, it told us that these two things react to form this. Okay, that's what it said, but it's not balanced, so we'll balance it out. 3 hydrogens for every 2. We'll create 2 ammonias. We third have to calculate each product to the same endpoint. There's only one endpoint, so that's easy, ammonia. And if you look at this, 300 grams of hydrogen will produce 1,700 grams of ammonia, and 1,250 grams of nitrogen will produce 1,520 grams of hydrogen. Okay? The 1,250 was actually the limiting reagent that produced the lead. Okay? Based upon this, this is the theoretical yield. Theoretically, this is the most you could ever make. Okay? Doesn't matter that you have more hydrogen, you can't make that amount. This is the largest amount that we can mathematically calculate that you would actually make. Now, the last question says, all right, we know we're going to use some hydrogen, but how much is left over? Well, what we have to do is make a relationship. How much hydrogen is needed to react exactly with that nitrogen? So I can do that. I can set up the 1,250 grams of nitrogen, okay, and relate nitrogen to hydrogen, and then calculate that to react 1,250 grams of nitrogen, you must use 269 grams of hydrogen. Okay? And it will be completely done. But I didn't ask how much hydrogen was used. I asked how much was left over. If you start with 300 and you subtract 269 that I must use, 31 grams is what the excess amount that was left over. Okay? And so, once I found the limiting reagent, which is normally the question, okay, which one is the limiting reagent, how much can you make? I could ask you one additional question: how much of the excess reagent was left over after the reaction went to completion? Okay. Okay. Let me show you one other thing before we do examples. Something called the percent yield. Percent yield is basically your grade on a reaction. Okay? So theoretically, you're supposed to make 100 grams. But at the end of the reaction, you made 42 grams. Is that good? No. Your yield would be 42%. If you got 42% on your test, would you be happy? No, you wouldn't be happy. All right? But you will find, if you're in organic chemistry and you get a 42% yield, that's super spectacular a lot of times. Okay? And so sometimes yields aren't what you expect them to be. Very rarely do they ever go to 100% in the organic laboratory or in the chemistry laboratory. All right? That changes, though, when you're in your body. Almost every reaction in your body goes to 100% completion. Very interesting in how we're designed. Okay? And so, a lot of times I will ask you what the percent yield is because I will tell you, at the end of the problem, you actually made 5 grams. But you then have to calculate what the theoretical yield is, just like we did, starting with what we needed, going to something produced, and then you take what you actually made divided by what you should have made times 100, and you get your percent yield. Okay? So here is a very long example of that. Okay? So the reaction of C6H12 plus oxygen, we're going to burn it, creates a compound plus water, very long compound then, okay, the acid itself. Assuming that you can carry out this reaction starting with 25 grams of the cyclohexane, which is C6H12, and that cyclohexane is the limiting reagent, what is the theoretical yield of the acid? Okay, well, oh, good night. Well, this one at least started us with only one starting place, 25 grams of C6H12. All right, I'm going to change grams of C6H12 into moles of that. C6H12. That doesn't even look like a 12. And then I'm going to go moles of C6H12. H12 to moles of this acid. I'm going to do that rather than write it all out. And then I'm going to say the moles, that isn't moles, that's no, of the acid is grams of the acid. Oh, wow. Okay, C6H12. All right, carbon weighs 1201 times 6 equals 72.06. And hydrogen weighs 1.01 times 12, which is 12.12. And that gets down to 72.06 plus 12.12 equals 84.18 is one of those. All right, going from the balanced equation, I take two of these to produce two of those. All right, the last. Okay, I have 10 hydrogens total times 1.01. So hydrogen, 10.10. I have 6 carbons. Oh, I got that down there. That's 72.06. For the oxygen, I have 4 of those. So 16 times 4, 64, plus 10.10 plus 72.06, 146.16 is in 1 mole. Okay, now let's go for it. 25 divided by 84.18 times 2 divided by 2, don't have to do that, times 146.16, 43.41 grams of the acid. Of the acid. All right. I was supposed to make 43.41 grams. I made 33.5. 33.5 grams. That's what I actually did. Mathematically, on a piece of paper, I should have made this. Oops. Well, if I put the right numbers in, it would be helpful. Times 100. No, that doesn't. That's not right. 33.5 divided by 43.14. That's better. 77.2%. My percent yield would be 77.2% based upon starting with 25 grams of cyclohexane and only producing 33.5 grams of the acid when I should have produced 43.41. Oh, the joy of this problem. Okay, let me show you the teacher's joy of this problem. Okay, to get a percentage, I assume that you can take what you're given divided by what you're supposed to get, right? But I didn't give you this. I made you do this whole thing to find out what the theoretical yield was, which made you practice doing molar mass and getting a ratio from the balanced equation. The only thing I didn't do for you is give you this equation where you actually had to balance it yourself. And if I didn't give you the balanced equation, that would have been a perfect problem to let you practice just about everything that we did in this chapter, with the exception of maybe calculating a empirical formula. Okay? And so this is an integrative problem that puts everything together. Okay? And so I could give you something as simple as this. If you should have formed this amount, but you actually formed that amount, then you take what you actually formed divided by what you should have formed times 100, and you get your percent yield. And that's a very simple problem. Okay? But why give you a very simple problem when I could give you something like this? Oh, come on. Do it. When I can give you something like that. You know? Teachers are just mean that way. We are. Okay? And so, here's a problem that you can work on about percent yield, which has all of it. All of it. Imagine, just like that. Imagine that you're working on ways to improve the process by which iron ore containing Fe2O3 reacts with carbon monoxide gas and is converted into iron and carbon dioxide. In your test, you carry out the following reactions on a small scale. If you start with 100 grams of the iron 3 oxide as the limiting reagent, what is the theoretical yield of iron? If the actual yield of iron in your test was 87.9 grams, what was the percent yield? What's the first thing that you do? Write down the equation. My equation is I have Fe2O3 plus what? CO. Yield. What? Fe plus CO2. All right. Is it all balanced? No. Okay. On this side, how many irons do I have? 2. And on this side, how many oxygens do I have? Or let's see, on this side I only have 2. Wait a minute. So that would, I can put a 2 in front of there, but I think we're going to run into something. Yeah, we are going to run into something. Okay. We're going to run into a carbon issue. Because over here I have 4 oxygens. Oh, oxygen is the booger. All right, let's take a look. If I do that, this one's not as easy. Because if I put a 2 in front of there, that's fine. But I got to put a 2 in front of that to get up to 4. That ain't going to work. Okay. Do 3 where? If I do 1 here, it doesn't work because I only have, if I do 1 here, it doesn't work because I got 4 oxygens. If I put 2 here, okay, that means I've got to put 2 here. That doesn't work out with oxygen. If I put 3 here, let's see if that works. What if I put 3 there? Okay. What do I have to put right here? 3. Carbons are good, right? How many oxygens are here? 6. How many right here? 3 plus how many right here? 3, 6. And then iron, I have 2 here. I put 2 there. That was not an easy one, even though it looked simple. Okay? First thing, write the equation. Second thing, balance it. That's why we give you 20 balancing things. Third thing, what do we do? Convert what to what? We go from how many grams of iron 3 oxide will produce how many grams of iron. Because we want to find out, starting with one of the reagents as the limiting, what is the theoretical yield? How much iron could you make on a piece of paper if everything was perfect? Anybody come close? How many of these can I put on the test? Can I put 10 of these? That's a long test. Okay. There's a lot of steps. You will probably get a limiting reagent problem. Okay. And you'll probably get one that will have theoretical yields and the yield, the percent yield itself. But I can't put on a lot of these very long problems because way back when, just balancing the equation was a problem. So I'll probably put some balancing equation type of things on that exam too, right? And so, what you should be able to do is complete all of the homework at this moment in time. I expected you to be able to complete the balanced one before break, but you still have time. Right? And you should be starting to work on that's the number 2, which has a lot of limiting reagent type of problems and theoretical yields. Okay. When is the homework actually due though? Friday.